For today's lesson, we'll begin with our trig graphs, our basic sine and cosine graphs. With the sine graph, we usually mark off 4 nice values. In trig, you guys did degrees and radians. Remember, this year, we'll be working almost exclusively with radians. So we'll label them pi over 2, pi, 3 pi over 2, and 2 pi. And then we'll have 1 and negative 1 on our y-axis. Remember, the sine graph always starts at 0, then goes up to 1, back to 0, down to negative 1, and then back to 0. For the cosine graph, we'll have the same labels. The cosine graph will start at positive 1, then going to 0, negative 1, 0, and then returning to positive 1. Next, we'll be finding exact values of trig functions. What's meant by exact value is if there's any radicals, we need to leave it in radical form. Now, in trig, you have to rationalize denominators. You should have seen in pre-calc last year, and it'll continue this year, that you don't have to necessarily rationalize the denominator. You can leave it with a radical in the bottom if you would like. If you still like to rationalize denominators, you can do that. So sine of 150, we'll draw our xy axis. 150 is in the second quadrant. So we'll put a reference triangle in the second quadrant. Remember, your reference triangles always come out from the origin and go back to the x-axis to form a right triangle. The 150 is saying that from here to the hypotenuse is 150. Well, we know from here to the x-axis is 180, so therefore we're falling 30 degrees short of 180. So 30 is our reference angle. This must be 60, and then we have 90. We saw in the last video that across from the 30 is 1, across from 60 square root of 3, across from 90 is 2. And then you just work off your reference angle, which in this case is the 30. We're doing sine, so we'll do opposite over hypotenuse. So we'll have 1/2. Now, one thing we have to label in our picture, which I didn't label here, it didn't end up playing a role, is anytime you move left or down, we would need to label them negative. So the square root of 3 would really be a negative value. The reason for that, if you were to just label your marks on your graph, this would be 1 and 2. This would be 1 and 2. But now this would be negative 1 and negative 2, and that'd be negative 1 and negative 2. So anytime you move left or down, we would need to make them negative. The hypotenuse is always positive. What that takes care of is that takes care of your ASTC, the fact that all of them are positive in the first quadrant, just sine is positive in the second, and the others are negative. Tan is positive in the third, the others are negative, and cos is positive in the fourth, the others are negative. So by labeling your sides that go to the left or down negative, that takes care of your ASTC. Cos of 225 now, that would be in the third quadrant. We are going beyond 180. We always work off of 180 or 360. We have gone 45 degrees beyond 180, so 45 is our reference angle, meaning we have a 45, 45, 90 triangle. Across from our 45 should be 1. They are each negative 1 because one of them moves left from the origin, one moves down. And then we know our hypotenuse is square root of 2. We want cosine, that's adjacent over hypotenuse from our reference angle. So we will have negative 1 over square root of 2. And again, you can leave it just like that this year. Now, some other exact values. Sine of 45 would be in the first quadrant. We'd have 1, 1, and square root of 2. Positives for the 1s because we're going right and up. Opposite over hypotenuse would be 1 over square root of 2. Tan of 60, that would also be in the first quadrant, but we'd have a 60-degree reference angle. Opposite over adjacent from the 60 would be square root of 3 over 1, so we just have square root of 3. When you have the multiples of 90, so 0, 90, 180, 270, 360, we want to look at our curves that we just drew 2 slides ago. For cosine, we want cos of 180. Well, that's the same as our pi. So if we sketch in our graph, pi is down at -1, so cos 180 is -1. Tan of 270, keep in mind we know that tan is sine over cos. So this is really sine of 270 over cos of 270. Well, looking at our graph, 270 is the same as 3 pi over 2, so we know we're going to have a 0 on the bottom. Anytime you divide by 0, that is undefined. So we don't even have to find out what sine 270 is. It would be -1 if we needed to know, but we can just say it's undefined because we know we're dividing by 0. For tan 120, we would be in the second quadrant. If this is 120, we are falling 60 short of 180, so therefore 60 is our reference angle. Across from the 30, we'd have a -1 because we're moving left. The 60, we have square root of 3, and then we have 2. So tan is opposite over adjacent. We'll have square root of 3 over -1, so that's a negative square root of 3. Sine of 330, that would be in the third quadrant. If we're saying here to here is 330, remember we work off of 180 and 360. Well, we're falling 30 short of 360, so our reference angle will be 30. We'll have a -1 across from it because that side is moving down. We've got square root of 3 and 2 for the other sides. We want sine opposite over hypotenuse would give us -1/2. And to finish it off, cos of 315, also in the fourth quadrant. If here to here is 315, that means we're falling 45 short of 360. So 45 is our reference angle. Across from our reference angle, we have a -1 because that side's going down. Across from our other 45, we have a +1 because that's moving right. And our hypotenuse is square root of 2. So now cosine adjacent over hypotenuse would be 1 over square root of 2. That makes sense. Cos should be positive in the fourth quadrant. The conversion between radians and degrees. We know pi radians is the same as 180 degrees. So we can always set up a proportion. We can do pi over 180 equals your radian amount over your degree amount. Now either the radians or the degrees can be an x, whichever you're solving for. Most often you use this when you are going to degrees to radians. If we want to know 135 degrees, we can do pi over 180. We don't know our radians, that's what we're trying to find, over 135 degrees. And now we'll just cross multiply. So we'll have 135 pi equals 180x. Remember, we're solving for the x. I see a lot of people start to get pi by itself. We'll divide by 180 to get the x by itself. And we want this in terms of pi. So we'll just do 135 over 180, which will give us 3/4. So this is really 3 pi over 4. If you have a radian that has a pi in it, we can just replace the pi with a 180 to give us our degree value. So we'll have 4 times 180 over 3. 180 divided by 3 is 60. 60 times 4 will give us 240 degrees. If you happen to have a radian that did not have a pi in it, you would just use your proportion. You'd put the radian number in the numerator on the right-hand side, and you'd put x in the denominator on the right-hand side, and cross multiply. Some helpful ones to remember, your radians 2 degrees. 0 is just 0. 90 is pi over 2, because that's like saying 180 divided by 2. We already said 180 is pi. 270 would be 3 pi over 2, or 1.5 pi. And then 360 would be 2 pi, because 2 times 180 is 360. Now your special right triangle ones that we'll see a lot, 30 is pi over 6, because that'd be 180 divided by 6. 45 is pi over 4, because that'd be 180 divided by 4. And 60 is pi over 3, because that'd be 180 divided by 3. Those are the ones that will come up most frequently throughout the year. All right, so we want to find the exact value. Even though we're given radians, it's usually easiest to think about in terms of degrees. So we're going to switch these to degree values. So this is really 3 sine. If we put 180 in for pi, 180 divided by 3 will give us 60, then 60 times 2 will give us 120. So we're really doing sine of 120 degrees, plus 4 cos, and if we put 180 in place of pi, 2 times 180 gives you 360 degrees. So we'll have 3 times, we'll go off to the side and do sine of 120. If here to here is 120, we are falling 60 short of 180, so 60 is our reference angle. Across from the 30 will be -1 because we're moving left. Across from 60, positive square root of 3 because we're moving up. Hypotenuse is 2. We want to do sine, so we'll have opposite over hypotenuse, giving us square root of 3 over 2. Now cos of 360, we can use our curve. Cosine starts up at 1 and gets back up to 1 at 360. So cos of 360 will just be 1. 3 times square root of 3 over 2 will just give us 3 square root of 3 over 2. And then we'll have plus 4. And it's perfectly fine to leave your answer just like that. Okay, that's an exact value because we still have our radical in there. Some other exact values, if we want to find secant of 5 pi over 4. Well, sub in your 180. 180 divided by 4 is 45. 45 times 5 will give us 225. So we're really doing the secant of 225 degrees. So we'll go off to the side. 225 is third quadrant, sorry. Here to here is 225, so we went 45 beyond 180. Each of these would need a -1 because one of them is going left, one of them is going down. Secant is the reciprocal of cosine. So we're looking for hypotenuse over adjacent. So we'll have square root of 2 over -1, which would give us negative square root of 2. For the other one, cosecant, we'll put in 180 for pi. 180 divided by 4 is 45. 45 times 3 will give us 135 degrees. Off to the side again, 135 would be in the second quadrant. If here to here is 135, we're 45 short of 180. The adjacent side would be -1 because it's moving left. The opposite side would be 1 because we're moving up, and we'll have square root of 2. Cosecant is the reciprocal of sine, so we're looking for hypotenuse over opposite. So we'll have square root of 2 over a positive 1, so this will just be positive square root of 2. That's it for finding exact values. We're now going to prove identities. You should have done this in pre-calc. If you're in Regents pre-calc, it would have been usually around March or so that you would have done it. When you prove an identity, you leave one side alone and just work with the other side. The side you're working with, you need to have equal to the opposite side. Usually it's easiest to work with the side that has more stuff going on. So we're going to work with the left side in this one and try and get it to be sine squared x. Now when doing these, we're going to use our reciprocal properties, quotient properties, and Pythagorean properties. We'll also just do normal things you would do in regular problems. Like if you have, in this one, something in front of a parenthesis, we're going to distribute it. If you have fractions that are added or subtracted, you're going to get a common denominator. So the same type of things you would do in a regular problem you would do when you have trig functions. So we'll distribute our cos theta. So we'll have cos theta times secant theta minus cos squared theta. Well, secant theta is just 1 over cos theta. So we'll have a cos theta that will cancel out, and we'll be left with 1 minus cos squared theta. Well, our main Pythagorean property is sine squared theta plus cos squared theta equals 1. If we subtract the cos squared theta over, that gives us that sine squared theta is equal to 1 minus cos squared theta. So therefore, we can just replace our 1 minus cos squared theta with a sine squared theta, and we have shown that that identity is true. Next one, we've got a sine squared theta over 1 minus cos theta. The fact that we have a 1 minus cos theta and that we want to end with a 1 plus cos theta leads you to think we might have to adjust and replace sine squared theta. Well, we just saw in the previous one that sine squared theta plus cos squared theta equals 1. And that if we subtracted the cos squared theta over, we got sine squared theta equals 1 minus cos squared theta. So we can replace our numerator on the left with 1 minus cos squared theta. Well, off to the side, imagine if we had 1 minus x squared. That could be factored into 1 minus x and 1 plus x. Well, we have that here, just the x happens to be a cos. So we're going to factor into 1 minus cos theta and 1 plus cos theta. All over 1 minus cos theta. Notice we have a 1 minus cos theta that will divide out to 1. So we're left with just 1 plus cos theta, which is exactly what we wanted. Next, we've got a 1 plus secant theta equals cos theta plus 1 over cos theta. You can work with either side. Remember, sometimes it's easier to work with the side that has more stuff. So we're going to work with the right side for this one. What we're going to do is we're going to rewrite this as cos theta over 0, or sorry, cos theta over cos theta plus 1 over cos theta. Well, cos theta over cos theta is 1. A 1 over cos is just a secant theta, and that's exactly what we wanted. If you had chosen to do the other side, you would have done 1 over secant theta is 1 over cos theta, and then gotten a common denominator, and you would have ended up with the part on the right. So this one, you kind of could have started with either side, and it wouldn't have been too bad. Next, we got tan theta plus cotangent theta equals secant times cosecant. Well, we know tan theta is sine theta over cos theta. That's one of our quotient properties. And cotangent is cos theta over sine theta. Notice now we're adding fractions. When you're adding fractions, you want to get a common denominator. So we'll multiply top and bottom here by cos theta. Oops, sorry, by sine theta. And over on the right, we need a cos theta. So on top, we'll now have a sine squared theta plus a cos squared theta all over sine theta times cos theta, because we want to get it as a single fraction. Well, we know that sine squared theta plus cos squared theta is just equal to 1. So we've got 1 over sine theta times cos theta. If you don't see it right now, you could break this up into 1 over sine theta times 1 over cos theta. 1 over sine theta is cosecant theta. 1 over cos theta is secant theta, which is exactly what we wanted to show. That's all for this video. We'll see you next class period.